Good morning, everyone. Good morning. So it's a great pleasure for me to introduce our speaker today, Mr. Guy Tamir, who is going to talk about open software for the parallel heterogeneous future, which is a topic that we elaborate on in this course. And this is obviously a subject in which we should be deeply interested, because introducing this kind of SIMT parallelism as easy as possible to applications is crucial in the new era of heterogeneous computing involving both CPUs and GPUs. Our speaker, although having spent almost his entire career in Intel, served in multiple senior roles. Today, Guy Tamir is a technology evangelist at Intel Software and Advanced Technology Group. His main areas of interest and expertise are AI, computer vision, video processing, but most importantly for our talk is heterogeneous multi-accelerator parallel computing. In addition, Guy is an active YouTuber with the OpenVINO and oneAPI video channel that just passed 3 million viewers. So I hope you will watch him again very soon. So please join me in welcoming Guy. Guy, the stage is yours.
Okay, so I'll speak English. I'm not a native speaker, so feel free to ask me questions in Hebrew, okay, or any other preferred language. Yeah, that's my role today. I'm a technology evangelist. That means that's a term from Christianity, right? To evangelize. I asked them to call me a technology rabbi, but they didn't like it. So it's an evangelist. That's my role, to spread the rumor, to look at new technologies, work with customers, stuff like that. My YouTube channel, I'll leave it to you later if you want to just go into YouTube and type oneAPI. Feel free to connect with me on LinkedIn. I'm approachable. I like to interact. And I think the most, what bothered me most when I was in my first degree was I didn't get how it's all connected to the real world. Okay, how these integrals and all this linear algebra really, matters to anyone. And this is one thing I want to show to you. I mean, my world, our world, how it's all connected, and the world has many problems to solve. Okay, you see it just recently. The price of energy is going very steeply up. We're trying to find new resources of energy, new, more aerodynamics airplanes. Trying to map the human genome faster to get precise healthcare. Okay, to find vaccination faster. Okay, you all saw the implication of that in our life. And the one big thing that really is united to all of these workload, all of these problems, is that they all need a huge compute demand. They all need, compute demand that, it's very, very difficult to really supply. So for many years, our guiding, criteria, our guiding beacon was Moore's law. Okay, so Moore's law was talking about multiplying the number of transistors. Okay, it didn't talk about performance. It didn't talk. I've seen, variation of this prediction to predict almost anything, right? The number of pizzas, I don't know, on the planet, but this is something we're trying to meet. The whole industry is trying to meet for many years. It's not easy for us. Okay, you figure, getting to 2x every about two years. It's not easy, but an example of neural networks, okay, with the introduction of AlexNet, and then the appetite for more compute, okay, is just growing in a faster pace, okay, than even Moore's law, okay. So we got data scientists, and they just say, okay, let's add a few more neurons, let's add more layers, and the compute demand is just something far from what we can actually supply. And these are neurons, when transformers came and the building block is becoming a huge monster like transformer, let's put more transformers in parallel in serial, and it just, the demand is just skyrocketing. I just talked yesterday with somebody, a customer of ours who's trying to run some, derivation of some model of like GPT-3, and he claimed that just to train it, they need about 20 A100 machines, right? A100 machines cost like a car. I don't know, it's 100,000 shekels, something like that. So he needs like almost 20 of them, and it takes him like 3 full weeks just to train the model. Okay, so the demand is really something out of normal, something that Moore's law cannot supply in any manner. And I want to talk about not only AI. I mean, AI is one example that I just gave, but there's so many things that are happening, so many very, very different kind of workloads. Okay, now when you try to map the requirements, okay, of each of these workloads, you see that they all need totally different requirements. Okay, some are memory bound, some are compute bound, right? If you're doing stock trading, right, algo trading, you want to get the result as fast as you can, right? And people are renting assets next to Wall Street just to get a few more picoseconds. Okay, so and if you're responding to cyber attacks, the same. You want to fast respond, so latency is the king, right? If you're processing huge amount of data like videos, you care about throughput. Okay, you want to make it as wide as you can. So it's totally different requirement from here to there, and we already understand that there's no one solution that fits all. There's no one machine that I can give you and will be best for each one of them. Okay, and I want to talk about 3 approaches to solve this huge demand. Okay, I want to talk about parallel, distributed, and heterogeneous. Okay, the 3 of them, and I'll start with parallel. Okay, so you've seen this. I think this is like the first lecture. You've seen Moore's law, and next to it, you've seen the single thread performance. And by the way, I think the frequency and power, these 3 just go together. Okay, power limitation. You're sitting with a laptop that eventually, it has a power density like a rocket or something like that, rocket engine, and we cannot dissipate that. And it all derived from that, all kind of limitation. And then at 2007, and by the way, around 2007, something really happened in the world. I don't know, you can read about it, but in 2007, something happened. Okay, Facebook, Twitter, iPhone, all of these happened around 2000. Read about it, it's interesting. But, and I am proud to say that I'm one of these dots here. The first time that Intel actually designed a dual core processor happened here. But somewhere it stopped. Okay, so somewhere you can see here, I think this dot is about probably 50 cores or something like that. So we have 50 cores on a single die, but it's somewhere stopped. So this is parallel. Okay, we have parallel applications, we have parallel computers. Okay, but it ends, and the question is what's next. Okay, and I'll try to answer it in a minute. And the best example for me to talk about parallelism is probably Fugaku. Fugaku, Japanese name for Mount Fuji. Until recently, the world's #1 supercomputer. They took parallelism to the extreme. Okay, they have like, I think around 8 million cores. It's a very small core. It's ARM cores. Okay, and they have 8 million of them connected together. And the big thing is their ability to actually break a problem into 8 million pieces, right? Calculate them in separately, and come back with a result. And they got a huge tailwind and nice success with COVID simulating particles in the air, and tell us all how we should be 2 meters from each other, or what the capacity of a train that is recommended, like you see here. And this was done on this highly parallel supercomputer, and there's some limitation. There's always a limitation. How much we can actually parallelize a problem. There are eventually dependencies in between, and how big such a computer can be. And which brings me to the next thing, which is if we cannot build bigger computers, let's just take smaller ones and connect them. Okay, and we know how to do that. The world is getting there. Okay, so like it or not, we have a supercomputer in our pocket, on a watch. Okay, and then the street lights, is another computer, refrigerator, and cars, autonomous cars with multiple cameras running around the city, and then communicating that there's an accident here, or there's even a trash can being here that has to be replaced or emptied. So we got multiple devices. Okay, the whole world is one big device, connected, computing, okay, to each other. And it's not only that this is not really the topic of this course, but I think it's interesting to know this one way to tackle this supercomputing problem. And it's not only that the hardware is highly distributed, the software today is highly distributed. Okay, so if and I took here just a small example. If I want to build an online store, okay, so I need a user interface. You need to securely log in. You need to search the catalog, check out, and so on, right? So it's all good. And if I'm building this to multiple operating systems, I'll need to rebuild it again and again, compile it to each one of them, of course. And if there's a bug here, I'll need to stop everything, right? Get a new version, publish it, and there's a new version of the operating system of this. Again, I have to do so. It's all one big chunk of software, sometimes too big to maintain, too big to move around. And the truth is that people are not really today building software from scratch, right? They're all using ready APIs. There are tons of them, millions of them. And if you want to do anything, okay, you have ready APIs for almost anything. If you want to do secure login, okay, it's not like you're going to actually right now thousands of lines of code to do all of it. You're going to take the API, which might have only, 5 functions, right? Like get a new user in, take a user out, here's a user, can I get him in? Stuff like that. So it's one line of code, okay? It's easier, it's simpler. This is how people code today. There's no need to rewrite it, right? So I bring the API, and what usually happens in technology, it brings his friend, okay? So the API is nice, but he brings the libraries he needs, and then all the other software dependencies, okay? And this is true for almost any of the APIs that I need. So I end up with a software stack, okay, for each of the functions that I need. And then each one of them might, be working or designed for specific operating systems, specific devices, only CPU, only GPU, etc., etc. So it makes a lot of sense to make each function here totally independent, right? And by the way, it can run anywhere. And there's a broker that, there are protocol so they can interact with each other. So my software end up to be something like that, very, very distributed. And each of these functions can run anywhere, okay? And it gives you a lot of robustness, okay? It communicates to the other world. For example, if my shipping department is down, there's something wrong with it, I can invent a new microservice that is just accumulated in the shipping queue. And then when the shipping is up, I just, flash everything to the shipping and so on. So it's much more robust, okay? You can locate it geographically anywhere you want. And it's happening today, right? When you log into Amazon.com, for example, okay? You think you see a web page, but what you actually see underneath, you operate like 100 or more than hundreds of small microservices. Okay, one of them will bring your login, one will bring the, your shopping preference or history and stuff like that. Okay, so it's already there. The problem is, this is a method to break the software into pieces, okay? And what we care about, at least in this course, is the big problems, okay? The stuff that cannot be broken, right? The kind of problem, okay? Like fusion, okay? That you really need a huge simulation, okay? And again, if you're building a supercomputer with 8 million cores, right? Why do we need them all together, for example? Okay, so the reason we're building a huge supercomputers is for stuff like that. Okay, for a simulation that has lots of dependencies. And I don't know if you've seen that there's a nice improvement that happened just recently in Fusion. We're trying to build our own little sun, okay, and create, you know, a new source of energy. This is the stuff that would really change everybody's life, but it needs this huge computation, which brings us back to this huge workload and compute demand and so on, and to what next, okay? So let me take all of these workloads, okay, and try to run them all on a CPU. And I'm gonna get for each one of them some performance, okay, because CPU can run everything, okay? Whatever you give in, it can run. But if you have a very specialized workload, let's talk about 3D rendering, for example, right? And you have a dedicated, you know, built-in architecture, the design to do exactly that, okay? Whatever your CPU is, it cannot compete with the efficiency that a dedicated hardware that was designed for that can do, okay? And the same goes for AI, for example, okay? So we got now, Intel got Gaudi 2, for example, and there are other accelerators. It might only can do 2 workloads. It can run only PyTorch and Tensor, maybe, but it will run it in very, very high efficiency, something that you cannot compete. So it makes a lot of sense, okay, to really use these accelerators. This solves our problem right away, right? Take the workload, at least the specialized stuff in there, and don't run it on a CPU, run it on a specialized ASIC, okay, and a hardware that was designed specifically to that, okay, and this solves the problem. Now, the truth is that you don't, you know, it's not you cannot use only a GPU. You need the CPU and a GPU. You need a host, right, and you need an accelerator usually to cover the full range of applications. And you know, you don't have to go very far. Our laptops are heterogeneous systems, okay, it has CPU, GPU, and more, and we see today, and we're going to see more and more hardware that, you know, specialized hardware for specialized workloads, okay? And this is just stuff that Intel come up with, like CPU, GPU, FPGA, deep learning, blockchain, and others, and I see so many of them, okay? Today, the big tech companies that have business needs, okay, also have, since they have so much money, they can design their own chips, right? So you can see Amazon building their own, you know, servers, okay, server chips, and you see YouTube. I think 2 months ago I saw an article about YouTube building their own, you know, video processing chip, right? And that's okay. That's okay. We will see more and more, okay, such specialized hardware for specialized workload. And you know, one of the things we're doing in Intel, for example, is building such a supercomputer, which will be heterogeneous. You can see here 2 Sapphire Rapids, 2 next generation Xeon processor, alongside 6 Ponte Vecchio, our next generation GPU. It's not really a GPU, it's a general purpose accelerator, okay? And you take these blades, you put many of them together, and we put in like 50,000 GPUs alongside 20,000 CPUs, something like that. So it's a huge machine that can do 2 exaflop. 2 exaflop.
8 million.
How much?
8 million CPUs.
8 million?
8 million CPUs. Maybe that means core. Maybe CPU is
okay, see, cores it's different. This 20,000, each one of them might have 20, 30 cores inside, right?
Yeah.
But devices, I think there are 50,000 GPUs. It's anyway, it's a number that we not easy to comprehend, right? And this is how it looks like. Okay, it's a big machine that we're building right now. It will be up and running in about a year. And exaflop is like 110 to the power of 18 floating point operations per second. It's a big number. The problem is, okay, if I am a developer, okay, somebody who's going to work on Aurora, okay, on this computer, okay, I don't really care if you have the CPU, GPUs. I want to code. I'm a scientist. I want to code, right? I'll tell you more than that. I want to see the next generation or the previous generation take the code from them and just improve them, right? They cannot recode from one generation to the other. They have to reuse the code, right? Now, if you look here, every few years you have a new generation for a different lab, but these ones have CPUs for AMD or CPUs from Intel, GPUs from AMD or NVIDIA or Intel, right? So it's a big issue for them, okay? The whole, thing of being able to port your software, okay? Software portability is a big thing, okay? Now don't have to go to supercomputers. I mean, this is the topic of this course, but this happens everywhere, right? Think about you watching Netflix on your widescreen TV, okay? And then you take it on your tablet, I don't know, to the living room, and then you continue to watch the video, the movie on your phone, right? These are three totally different platforms, okay? Today, what it means is that you have to take the code, almost the same code, and recode it, recompile it for each of these platforms, right? And this is not what we want to do. This is not very productive, okay? So, and the problem is that, like I said, these devices is totally different. They're built totally different. Look at CPU, for example. Okay, CPU, and I just threw something here. I don't know even which CPU this is, but this is the work. Okay, this is like if I want to do 1 + 1. 1 second. This is where it's done. But for me to get, for the instructions to get to the point where you actually do the calculation, sometimes there's an overhead of 90% of the work. Okay, I don't know if you've seen מבנה מחשבים, right? למדתם כולכם, נכון? So there's branch prediction. Okay, that's crazy thing. Okay, you have a branch. Okay, let's take right. There's another branch. Let's take right. No, you missed something. I need a cache line. Go, fetch it. Let's pre-fetch it. Let's make sure it's coherent across all the memory hierarchies and so on. It's a huge overhead. Okay, if you have a GPU, okay, a GPU, let's assume, knows only how to add. So you tell me, give me number 1, give me number 1. Here it's 2. Okay, so the work, it's doing most of the work. There's no much overhead of combinational, logic around it, how to get it, so it's really, it looks totally different. The work is totally different, and accordingly, programming it will look totally different. So the CPU will have a software stack on top of it, right? Like the driver, runtime, libraries, framework that was built specifically for this CPU to get the most out of the CPU. The GPU will have a totally different software stack on top for it, right? And it's totally different. Now, if I really want to be able to move code from one place to the other, I need some layer. It could be the framework, the application, the libraries, I don't know, but some layer that could help me translate, right? That could be understood, okay, by the CPUs and the GPU, for example, okay? How do we create that? It's not easy, but what we want to do, and this is a term that is used a lot in the industry, we want to take the code from here. We want to lift the code, okay, to a more abstracted way. And then we want to lower it to another hardware. Okay, now what's the problem? The problem is that when you go to higher abstraction, it's great, but you lose a lot of information about the code. Okay, I mean, the lower you go, you have to be more specific about the hardware. Okay, I'll show it to you in a second. I'll try to explain it. And A great example I saw about that is what Google is driving, which they call MLIR. I don't know if you've seen that, multi-layer intermediate representation. Okay, so you can code TensorFlow, which looks like here's a neural network. It has 6 layers, stuff like that. Okay, so it's really, really abstract. Okay, and once you go down, you have to add more and more hardware-specific information. Okay, there's a layer here which when you can say, you need to say, these are my registers, this is my memory, right? So, and basically what they're trying to do is exactly that. You can go up and then go down, right? And be able to port the code from one to the other. Okay, and I've seen many examples for that. For example, Helite, I don't know if you heard about that. They try to separate the functionality, okay, from the actual implementation. Okay, so you can say this is add, take A, add plus B, and the description, the hardware description for CPU will say take this register and do this operation. And the same for the same functionality, you're going to have another description for GPU or for FPGA and so on. So this is exactly what can help us, okay, port software from one device for the other, from one architecture to the other. And what we want to do, you want to work here, we want to program at that level, but we want to run here. Okay, we want to code to run here, and it's obvious why, because going up the stack means productivity. One line of code in PyTorch, can take you thousands of lines of code in assembly, but here it will run faster. And I saw a nice example here of somebody, I think he's just looking for prime numbers, and you can see here he's writing it in Python, okay? And he's trying to write the same code in C++. He finished coding in Python, and the same code in assembly, okay? So, and he's trying to compare both the programming time, okay, and the actual runtime, okay? So C++ code is done, and now assembly is done, and now we're just running everything together, and you can see that the C++ code is finished at 5 seconds. Assembly is not much better, and again, it will be totally different depending on the case. And if you wait long enough, you can see that Python took like 10 times slower. Okay, now this is exactly the trade-off I'm talking about. Okay, Python will be, for me, I can write this code in an hour. In C++, if it's a little bit more complicated with pointers, it will take me a few hours. In assembly, it will take me forever. I don't know. And it's not only that it will take me. Okay, you need an expertise that not too many people have. Okay, so you can easily find a kid, 16 years old, who can write Python. You need to be 20 to write C++, and I don't know how old you have to be to write assembly. But you understand, it's different people, different productivity, different runtime. And
it goes down, start with C, go to C++, and at the end you learn Python.
So people still write in assembly. I found it very interesting that when I go to the East, I go to China, they tell me, no problem, I'll call it in C or lower. When I go to America, to the US, they tell me Python and up. Okay, so everybody is, I don't know if it's, something cultural, but the productivity versus the performance is very clear. And this is something we're trying to solve. And you can see here, Python is written poorly. Okay, it's written for productivity. Okay, it's great. We have packages for everything. Okay, and it's done so fast. But it's implemented wrongly. I mean, because there's a price sometimes, right? If you want to take a variable and not define if it's integer or floating point or whatever, then I need to be prepared for everything, right? So the whole allocation of variables, for example, in Python, okay, is very expensive, okay? And eventually it's going to run on one core, okay, even if you have 100 core. So you can, this is an article I saw, where you see the speed up, and it's easy sometimes for us to take one application in Python and say we can do 10,000 times faster, okay? It's not that difficult because, of the way it's written. and how much we can actually parallelize it. Okay, and before I move on, okay, we talked about parallel, distributed, and heterogeneous. And I think a few weeks ago, Intel came up with a new CPU, Raptor Lake, that was designed here, and I think was manufactured in Kiryat Gat. And I'm asking, is it a parallel machine? Is it a distributed machine? Is it a heterogeneous machine? What do you think? Huh? Heterogeneous? Okay.
We're not both. We're not all.
So let me show you. Okay, this is the floor plan. This is a floor plan. I got it online. It's not because I work for Intel. I got it online. This is a floor plan, and I'll just show you a few things. Okay, first of all, they have performance scores. Okay, performance scores are supposed to work faster. Okay, in addition, they will have smaller cores. Okay, but you can see here 8 performance cores. Okay, and these are efficient cores. Again, many of them, it used to be a separate chip. It still can be found a separate chip on Atom chip, and the whole PCH can be found separately in another chip. Okay, this is, by the way, a small company from Yokneam that we acquired, I don't know, 10, 15 years ago, and now it's just a small logic inside. And the GPU, of course, used to be totally separate. It still can be sold separate. Media agent is another totally different logic. And there's more, okay? So you can see here, it's an integration of many, you can call it chips, okay? Many different logic, so it's totally heterogeneous. I don't know about distributed, it's all in the same place, but it's highly parallel, okay? And the only reason we don't talk about it in parallel computing classes, that it's all under the programming layer. It's all inside the ISA, right? I mean, for me, it's not very different than if you show me a cluster of this supercomputer that has two. So the only difference is, okay, of course, they're all together, and you can program them as one intrinsic piece of hardware. That's the point, okay? And I think if we go, it wasn't like that. A few years ago, this is what you get when you buy a CPU from Intel, right? So I think it's going to be even higher. Okay, we're talking about higher level of integration, putting together CPU and GPU and AI accelerator in one chip and so on. So you're going to see more and more stuff that is hidden from the programmer, okay, and being done automatically by AI, by I don't know. You're going to see that happening. Okay, so what we're looking for is we're looking for software portability. We're looking for the ability to program heterogeneous, meaning, system that have multi-accelerators, okay, preferably with open standard, open source, cross architecture, cross devices, cross vendors, okay? This is what we're looking for. And this is exactly what we're doing with oneAPI, okay? So oneAPI is an industry initiative where Intel is driving it pretty hard, but there are many people already involved and already like the idea. You can see your universities, but you can see here also all kind of commercial companies that are taking part. And the spec is open, the source is open. You go to GitHub and you see everything is there. And there are already packages of oneAPI all around. There's also the Intel implementation of oneAPI, okay, which I'll talk about in a second. And what it means to be oneAPI compliant is that, there is a software stack that is unified and can help you run the same application on multiple devices. And I'll show you 2 examples, okay? And this is great news for developers in my mind. This is great news for the world that's going to have many more accelerators that you want to really use, but you don't want to invest now half a year learning the actual architecture and the instruction set. You don't care about that, right? You can ask in Hebrew, by the way, and Israeli style, just burst in. Yeah. Okay. So oneAPI, and when you look into this, okay, it's really the components are. We have libraries that can work on CPU, GPU, FPGAs, and other. We have tools, compilers, and languages. Now, again, going to just show you some of them. Okay, so for example, talking about libraries, we got really all kind of libraries. Okay, libraries for communication, for for math operations, for rendering, whatever. So oneDNN, for example, is our neural networks. If you go to oneAPI.io, you go to the spec, you can actually read, see the open spec for all of these libraries, okay? And you can actually go and see the primitive, okay, the definitions. If you want to code it yourself to your specific hardware, it's pretty easy. If you go to GitHub, oneDNN, you can actually see the code, okay? It's the actual code, it's open source, okay? You got here all the explanation. If you go to the actual source, okay, and you choose, for example, implementation for GPU, for NVIDIA, for example, you can actually see here the full, you get here to, access to the full source code of this library on NVIDIA GPU. And in the same will work on CPUs by Intel, by ARM, and by many. By the way, Fugaku is using exactly this library for neural network, okay? And it's ARM based, okay? So this is really cool. And we have all kind of languages. So there's Python, optimized, and Fortran, of course. But I will talk a little bit more about SYCL. Okay, the point with SYCL, it's really C++ based. Okay, with I would say directives for a new way to code for parallel and heterogeneous systems. Okay, the bottom line is very simple. Once you have your code in SYCL, okay, which again looks like C++, I'll show you the code. You can run it on almost any CPU. You can run it on GPUs from Intel, whatever, NVIDIA, AMD, on FPGAs by Xilinx, whatever. Okay, so the code is now become portable. Okay, and the same code will run anywhere, maybe with minor changes. Okay, and I'll show you an example. Okay, and if you want to take your code, you have a CUDA code today, for example, you want to convert it, we have tools to generate this code. So this is an example which I'll show you later. And there's lots of examples like that of code that we just took CUDA code, okay, press, just operated the script and automatically got the code in SYCL, and now it's running. It can run back on NVIDIA card, but it can also run on other devices. And it makes the code just portable. And we have tools like and profilers like Intel Advisor, and I'll show you an example in a minute to help you if you have a C++ code. And that's a good question, right? I have a huge C++ code. Now, what can I offload? What do you recommend me to offload to a GPU, right? I mean, it doesn't make sense to offload everything on a GPU, right? But we have tools that can look at your code, analyze it, and tell you this function. If you run it on CPU, you're going to get 10x faster, even including the memory traffic there back and forth to the GPU and stuff like that. We know how to calculate it, so in advance which function you want to actually offload to an accelerator. A good stop for questions if you have.
Question for me is like, why does Intel want to have its competitors basically?
So 20 years ago, Google came out. I read an article by Google saying, we are hardware agnostic. You can run our code anywhere. And I was shocked. I said, what do you mean everywhere? Our hardware is the best, etc. And now Intel is doing the same. They tell you basically software will run everything anywhere, right? And the hardware will win. Choose your hardware underneath, okay? But software, we're trying to remove the barrier of, you can say that we're stupid. No, you can say that we're stupid. If you're cynical, you're going to say that we're trying to drive in a new GPU, and a lot of the code base is in CUDA, so we want to be able to open the standards so people can move easily to us, okay? But yeah, I think it's a good move, and it's definitely new. It's not something that I would imagine 5-10 years ago that Intel will go for. Okay, specifically not for a hardware company. Okay, we are a hardware company. Do you know how many software people works for Intel? You give a number. About 20,000 people. I mean, you can argue what is software. Firmware, microcode, you know, they're all layers, levels, but 20,000, I don't know the exact number. It's about 20,000 people. It's a huge software company. Okay, it's not Microsoft with 200,000, maybe, but today 10,000 less. But it's still huge. Okay, it's a huge company. We're doing a lot of things. Look, all of these stuff. We're working with Google for years. But people dedicated for optimizing TensorFlow on Xeon CPUs and now on GPUs. Okay, we're working with Conda, with all the suppliers of Python packages that we care about, and there are hundreds of them. We work with Facebook, with everybody. Okay, and you can imagine that we're working with Windows, you know, with Microsoft and Linux Foundation and stuff on the lower level, but we're going all the way up to very high level software. Okay, and the reason is because you as a programmer expect it today. Okay, like 20 years ago, I could just give you a piece of silicon, give you a sheet of paper with the spec, go do something. Today it doesn't work, right? Today, if you go to a startup, they want results tomorrow. Get the package, get it working. I want to see a POC, okay? And yeah, it's a different time constant for developing, for everything. And by the way, if you are working for a startup and you have a nice application, at one stage, you will have to choose your hardware, okay? You have to say, okay, we're going with NVIDIA, for example, okay? And that will lock you into this path, okay? I mean, I've seen that. I've worked with companies who told me, look, I have zero time. I have it working on some NVIDIA platform, and that's all. Okay, what we're trying to do here is to give you the freedom, okay, to code in SYCL and then choose your hardware. You can still choose it later, okay? I'm just saying, okay. Okay. Okay, so we got lots of components, like I said, and we're packing them into toolkits. What time is the break? Now. Okay, so let's break. אתה מפסיק את ההקלטה באמצע? לא? אוקיי. בסדר גמור. We're not gonna break? Okay, no break. No break for you. No soup for you. Okay. Okay, so out of all of the base toolkit is great. I really like it. I just install it and I got everything I need. Okay, there's all kind of other toolkits, AI toolkits, rendering toolkits and stuff. But here I want to show you, for example, some components from it. Okay, I'm going to show you like 4 of them. And I'll start with the library, the data parallel C++ library. Okay, basically, we're adding heterogeneous capabilities to C++ with the library. Okay, so the best, easiest, fast way for me to show it to you is with a code sample. So I'm taking here a data. Okay, I generate random numbers just to initialize it, and then I sort it. Okay, this is C++ 17. Parallel STL, okay, add policy, execution policy to this library. Okay, so you can say run it sequentially. So one thread will only run for this. And now you can say, no, run it in parallel. And then you apply this policy, and this whole sort, which is the heaviest operation here, will run in multi-thread. Okay, what we did here is we added oneAPI policy. Okay, so it's the same code. You just have to change your policy. And now, okay, you can choose the default. For example, the default means that the sort operation will now work on GPU. Okay, so think about that. If you want to actually do sort on GPU, you have to take a CUDA course, okay, or something like that. You have to know what the actual architecture and the instruction set and so on. No, you code C++. You just tell it, run this function on the CPU or the GPU or whatever you. Okay, I think this is pretty cool. Okay, you already have a code, and this function is taking forever. Offload it to another device. Okay, I think it's a pretty cool thing. Very low investment. Okay, you can just take the oneAPI based toolkit. You don't need to change the code, and that's all. Okay. Okay. If you don't want to work in libraries, you prefer to work on direct programming. We offer SYCL. SYCL is basically C++ and extensions. Okay, and I'll show you. And data parallel C++ is basically the compiler. Okay, so it's based on ISO C++. So the ISO standard is single source. You don't have to write two codes, one for the accelerator, one for the device. It's asynchronous, event-based programming model, and we have many people involved and lots of things is happening. And if your C++ code would need to be compiled, linked, and then run in the CPU, now we still have the same compiler. We're just adding the ability to compile your device code, link it, and so on. Okay, so in the same program, and I'll show you in a second, you can just program the whole system in C++. And if you want to do heterogeneous computing, in my mind, this is what you need. Okay, you need device discovery. So you need to know what's in the system. Okay, think about the code. Okay, you send it to the cloud, and sometimes you don't even know what's underneath. What GPU do you have? What CPU do you have? Right? So you need to be able to detect in real time what device am I running on, and even the status of the device. Right? For example, what's the temperature of the CPU, of the GPU right now? Okay, you want to know all of these in order to make your program eventually run dynamically even. Think about that, okay? And I get lots of customers talking to me and saying, we're paying a lot of money for a GPU because we need, when we have a huge traffic, okay, we need GPU. There's no other way. But then it drops. And I don't need to run it on a GPU anymore. Can you just offload it now to a CPU based on the traffic, on the demand of the requirements, stuff like that? So I totally envision how it's going to, how in the near future, okay, we'll be able to take your code from this device to this device and optimize. And you can just tell us, optimize for throughput, optimize for latency, optimize for price. Okay, I want to pay as least as possible. I don't care if it's fun a little bit slower, right? But it gives you the flexibility. And for that, you need to know which devices are in the system and what is their status, okay? Number two, you need to control these devices. You need to be able to dispatch work to this device, right? Know, that it's finished, stuff like that. And then, not only the work, you need the data to work on. So you need to manage the memory between them, okay? And of course, CPU memory and GPU memory have totally different address spaces and memory accesses and stuff. And you need massive parallelism. Okay, so device discovery. Just an example. Okay, I can show it to you later maybe, but just get a platform and tell me which devices are connected. Okay, when I run this on my laptop, it immediately tells me you have all of these devices. Okay, you have a GPU, I have an integrated GPU, and so on. Okay, so it can detect whatever is on your device. Okay, and now, by the way, you can choose your device. Okay, so the way to communicate with the device is with a queue. They say I have an execution queue, and I want to take the host. Okay, so the CPU usually have a queue attached to it, and you can attach several queues to devices, and you can put work in the queue and just let the runtime manage the execution. And here, for example, if you go, you can now choose which devices you want based on the properties. Okay, for example, you can say, again, I have a software, and I see that a lot with ISVs, with the people who write software. This is the product. They don't supply you with a piece of hardware. They just say, this is my product, run it anywhere you want. But today, it doesn't happen. You have to run it on a specific, right, hardware specification. But then think about that my software can say, look, I need a GPU. It has to support, 64 floating point. It has to be only by, somebody, and so on. So once you have this insight into the system, you can even select your device based on all of these properties, okay? And this is number one. Number two is control the device. And like I said, you get a queue to a device, and then you submit the work to the device. So you write it all here. This work, this between these parentheses, this kernel, okay, will work on the device. What is the device? You decide. The same code can run here, can run there. It doesn't matter, okay? But this will run on the device. It's very easy to be done. And then number three is cross-device memory management. So here I'll give you an example of buffers, okay? So I define a buffer A, okay? And right now it's all on CPU, right? And here I need an accessor to access the buffer, but it's the same buffer that both CPU and GPU sees, okay? And this is, I find it's very elegant, okay? You define a buffer and you can access it from anywhere, okay? It's pretty cool. And underneath it, of course, there's you need to copy the data and stuff like that. You don't have to do that. The runtime is doing it all for you at the runtime, you know, at the right time, okay, to optimize the execution. If you insist of using one address space and not buffer, we support what we call unified shared memory. So think about that. We allocate memory here, okay? And data is, there's all kind of way to allocate the memory, but here I did it malloc shared. So it's the same malloc, okay? But it's shared. It's the same address space that is mapped to the CPU and GPU. And that's all. This data, okay, can now be used on the CPU, on the GPU, on whatever you, okay? I think this is very powerful. And one of the reasons we did that is because, you know, a lot of the code that you already have in C++ is built like that, all right? So it's very easy to just convert it to SYCL. Okay, and the last thing is massive parallelism, okay? So this is a serial code, okay? And I want you to argue with me about that. But, you know, whenever you have a loop, okay, by nature, it means go one by one, right? This is an iteration. Now, everything you're doing here in this course is, hey, I have a loop, but please run it in parallel. How do you know how to run it in parallel, right? Eventually, the compiler need to know. The compiler doesn't know lots of things, and he's always conservative, okay? He will not take any risk of corrupting your data, right? So if he's not sure, he's not going to run anything in parallel, okay? Safest for him. This is why you tell him, hey, this loop is parallel. That's okay, okay? And but this is different than here. Here, it might be, by the way, totally different people who wrote that, right? This is a scientist, okay, who knows what has to be done, okay? And then he said, this is running so slow, I don't know what to do. So he hands it over to people from Gal's department, right? For the people who actually know the hardware. And they will ask him, hey, this can this run in parallel or there's dependency? And they will say no dependency. They will add afterwards, right? This pragma, right? And all kind of directive. This is like directive-based parallelism. Okay, it might be different people. It might be iterative process, right? Where you imagine that you have a problem, and then you see how you can help the compiler understand better the code and parallelize it better. But it's still by nature, you know, serial. And this is a parallel code. Okay, what you have here is something that looks like a kernel. Okay, and the reason I can run this kernel, okay, this kernel is all I care about. This is a work. Okay, now this is a space it has to work on, and now you can decide how to run it in parallel, what order or whatever. But it's written totally different. The reason we can do that is because much of our work is parallel, right? Think about, it's always easy to me to look at the computer vision as an example. We have pixels. I want to do something with a pixel. For example, I want to blur the image. I want to run some, I don't know, average on this window, right? And I'm just going to look at a window, and now I can just run it all across the image, okay? But I don't really care what's the order, and I'm going to blur it, or I'm going to run another kernel and I'm going to sharpen it. But what you really care about is just designing the kernel, okay? And it's a different approach than people writing loops, okay? It's really by design parallel, okay? And still, you know, so it was built from the beginning, from the ground out, be parallel. It's built like C++, SYCL. So if you're looking at OpenMP, which works great with C and with Fortran, this looks a lot like classes, and object-oriented, and it's sometimes easier to code. I'm not saying that OpenMP is not good or something like that. Specifically, not in this course. Okay, my insurance is not going to cover this. Okay, but eventually we are able, okay, with SYCL, and I'll show you a few examples to port code, okay, from one device to the other. Now, there's a big difference between functionally porting code to keeping the performance optimized, okay, and that's a totally different story, okay. And you've seen that even if you're doing, I've seen that even on one device, okay, where you're using a kernel, okay, you're doing like computer vision, and the kernel fits in exactly to the GPU sizes, okay, it's great. Okay, if the kernel is a little bit bigger than your execution unit, then you have to do it twice, you have to synchronize them. It breaks everything. It breaks the performance, right? It's very delicate, and eventually we talked about that. As you go down, okay, you have to understand what the hardware looks like, and you have to map the software to the hardware resources in order to get the performance. But that's a different story. So SYCL is doing a great job in that, in my mind. And like I said, if your code is SYCL, it opens up all of these devices for you, and it's a nice opportunity. And I want to show you just one example. Okay, I ran this simulation. Okay, I took the CUDA code and I just ran a script, and it automatically converted the code to SYCL. So this code, I didn't write it. Okay, it was generated automatically. By the way, you can see here, for example, here, migrated API doesn't return error code, whatever. So there's lots of warnings, okay, in between, but it's all functional, it's working. And then you see I get default queue, and I submit a work to this queue. What is a default queue? Now, I can rewrite the code and write here CPU, get CPU queue, and write on CPU. And then get GPU queue and write on GPU, right? It's the same code. I only have to change this, okay? And the same code will run on CPU. I did more than that, okay? I didn't touch the code at all, and you're going to see that in a minute. I just changed the default from outside of the, using an environment variable, okay? And you can see here the CPU utilization. I just ran top, and the GPU utilization, and I'm running the n-body, the simulation on a CPU. I made the default queue to be CPU, right? And I'm running it, and it's basically a simulation that takes multiple particles and calculate. You see, it's running on my Xeon Gold on the CPU. Okay, it's running on CPU, 60 milliseconds. Okay, the CPU is using 11 cores. GPU is only running the graphics. Okay, so it's not doing anything more than that. It's sitting idle right now. Okay, and now I'm going to run the same code. I'm just changing the variable here, the external environment variable, that the GPU will be the default queue that I get with SYCL, and it's now working on my RTX 4000. You see, it's working 10 times faster. It's the same code. I didn't run it. I didn't change anything. I changed the environment variable from outside, and you can see that the CPU is hardly working, 2 logical cores, and the GPU is doing the computation and the graphics. Okay, I think it's pretty cool. Okay, same code that I can just choose where to run. I don't even have to touch it. Okay, I think it's interesting. I think it's cool, and I think it's definitely can help people. I'm going to run through this. So, like I said, we have tools to migrate CUDA to SYCL. It can do like 90% of the work automatically. The stuff that it cannot do, for example, error code is being reported differently on GPUs and CPUs, stuff like that. Okay, but most of it just works. It's just mapping the buffers allocation to SYCL, and you can see here all kinds of errors. Okay, maybe you need to rewrite this code, maybe, but many of the stuff I tried just worked out of the box, and it's working. Now, if you have C++ code and you asking yourself what to do with it and how to offload it because you just purchased a new GPU or something, then I think Internal Advisor is a nice tool. And I was surprised to see how powerful it is. First of all, it can analyze your flow. Just look at each function in the code as one entity and a graph that connects them and can show you the whole flow of the dependency. It can help you with thread prototyping. It can help you with vectorization. And I really like the roofline analysis. And basically, it's an analysis of the code. Okay, it first starts with looking at each of the function and calculating the arithmetic intensity. Intensity it basically means, how many operations you're doing, okay, per byte of data. But then, of course, you need to know how much data or how much each of these functions is used, right? So, you can basically put each of these functions when you actually ran the application on a graph, right? And say, this is the compute intensity, right? It's more compute intensity to compute cosine than to just add something, okay? Which is obvious. And you can also put them, on the right place based on the usages, right? This is used more than this and so on, this function. And eventually, okay, you want to map that to the system capacity, right? For example, this CPU is able to handle this amount of flops per second, okay? And there's also other limitations, for example, memory, okay? So the memory can only transfer this amount of data. And hence, here comes the roof, okay? And the roof line analysis. So basically, theoretically, each of these functions could be taken all the way up to the maximum potential, right? But this function, which can be easily or greatly improved, is hardly been used in my program, right? The function is been called once in a million years. So I don't care. Don't touch it, okay? It will not improve your overall application performance. And this one, I know that it's already optimized, okay? So focus on that. So this is exactly what Internal Advisor is doing. And by the way, it's a little bit more complex because it's a different limitation to scalar operation, vector operation, and there are different limitation if you're using the memory level 1, level 2, or 3 cache. Each one of them is different in speed, in capacity, and eventually this is how the tool looks like, right? It analyzes all of your code, put all your functions on this roofline analysis, and tell you, go here, focus on this function, okay? I mean, there's no other way to know what to choose. Focus here and optimize this. And moreover, we have an offload advisor that can tell you, I checked your code, okay? And I think there are 3 candidates to offload. You have to tell him which GPU, of course, right? I don't see it here. I ran it on a Gen 9 GP2. I don't know. I think I ran it on my laptop, but it can tell you exactly this is the number of functions. These are the functions. You can go and look at the code, and it's only 75% of the code that you can actually boost. You can boost these by 50%, but since they're not very widely used, it will improve the overall application by only 10%. Okay, but this is a nice analysis, right? That just look at your million lines of code and tell you exactly, take this function, put it on the GPU, you'll get 50%. Okay, so I think it's very powerful. It's a very nice thing. And all kind of offload, bound, it tells you, what really is an overhead here. For example, here, memory bandwidth, right? So you use a lot of data here, and the memory bandwidth will cost you most of the dollars to really offload this. Okay, and I think this is all I wanted to say so far. And like I said, YouTube, look for oneAPI. Feel free to connect me on LinkedIn, and I hope it was interesting.
We'll start the panel now. Okay, so we are starting a panel with questions from the audience, both here and Zoom. I would like to start with several questions that been submitted via Zoom. So the first one is either a performance comparison between oneAPI code vs architecture-specific code like CUDA for various architectures, and as we are at the end of the presentation, I will ask what is the difference and where we can see it.
So it's a very general question. Depends on many parameters, right? Depends on what you're doing, what is the hardware, what are you comparing, okay? So we have a few examples of SYCL code, okay, running faster than CUDA on NVIDIA GPU, but there's other examples. Okay, so I cannot generally say, it would be that the performance will be better or how much it would be worse. It really depends on what you're doing. We're still ramping this up, but one thing I can tell you for sure, it's going to be 100% portable. Okay, so
regarding portability, that's a question that I have. So you say that when you write the code with SYCL once, you can port it to any kind of hardware, and that's a great benefit. But in this course, we learned the contrary: how I can take any kind of code, not a code that's been built specifically to be heterogeneous, but any kind of code. It could be serial, it could be already parallelized, and to adapt it to be not hardware specific, or maybe to be hardware specific. Now, how do you see I would say, tension between OpenMP and SYCL in the today software ecosystem?
So OpenMP can do a lot of what SYCL can do, right? It's not everything because it can offload to heterogeneous devices, right? I think it's a question of eventually style, okay, programming style, ease of use, okay, and some people. This is why we're still using OpenMP. It will be used, okay, for a long time. And people who write Fortran and C will naturally use OpenMP, whereas people who are using C++ and use classes and objects and stuff will find it much more natural to use SYCL. Okay, so I think there's enough of the world for both of them. It's different styles, and eventually we'll have to see how it's all going to evolve. Okay, because people will have to fully adopt SYCL, see what's the strength of it. Okay, and by the way, it's still evolving. Okay, so it's a vivid community of people who are still defining stuff. Okay, so we have lots of examples of big sample code, and we're just building more and more code by the national labs, code by commercial companies who report that they can take code from CUDA or take code from CPU to GPU, and they run the same code on small IoT devices like DSPs, and they're using the same code. There's huge advantages that you can run the same code all around.
So if I'm summarizing that to me and to the audience, so it goes like that. If I already have, or I'm willing to build a large-scale C++ object-oriented code, so obviously the right thing to do is use SYCL. It will portable much better. It would be more elegant and more compact in many ways. But in the rest of the cases, when I have, I would say, sparse computation in the meaning of the count of actual lines in the code and the way it's been designed and built, and there is no object-oriented, or maybe there is a little bit of it, and you use different kind of codes, or you just want to not reprogram it and just put it directly, so you use OpenMP. So in that way, they are complement one another.
Right. So look, I have enough gray hair to know that there are multiple solutions, right? And Intel is for example, are supplying so much hardware, and I was shocked. I mean, I came from AI, and Python is the king, right? But we have $100 million, accounts that using Fortran.
Right.
Okay, most of the, by the way, of
So
that.
it takes me directly to the next question. Why we don't have SYCL in Fortran? Now, Fortran 2018. It's already object-oriented with classes and things like that. Why we don't have a SYCL for Fortran?
I think it's an implementation question, right? I mean, by the way, we're taking SYCL and wrapping it to be in Python. So you have parallel Python as well. If you prefer only Python, and there are all kind of tricks to do, JIT compilation to specific kernel and stuff like that. So you'll be able to use SYCL in Python. And again, the question is, how do you eventually implement it, right? And does the language eventually allow for parallelism, for acceleration, and so on? And some are more suitable to this, and some are more suitable to that. So we rely on all our children. Okay.
Hmm. Let's take a question for the audience. You have a question?
No.
Yes.
Intel is most known for the CPUs, right? So in this world, most personnel use CPUs more than enough. Yes, my computer, my phone don't need any more processing power. So most of the world now works on the GPU. So do you think Intel is some sort of troubles with the CPU isn't needed included before, so now they try to reinvent themselves in the GPU and NVIDIA world?
Okay, that's a good question. And there are lots of myths here that I would like to break, okay? First of all, who sells most of the GPUs in the world? Do you know?
Probably Intel, because it's
Intel is selling 80%. NVIDIA and AMD are selling together, I think, 20%.
What about GPU?
Don't worry on exactly. Right. Okay. So the first, the second you said about computation needs. Okay. So first of all, yeah, we see the need, and this is why we came up with discrete GPU. By the way, Intel had discrete GPU at the beginning. Okay. And then we integrated it. By the way, here down in Haifa, the first integration of GPU into the CPU was done here, and yeah, now we're taking it out again. By the way, due to multiple reasons, it's also.
So we refine the question and say how come that Intel somehow missed the GPU era over the last 10 years?
We have missed many things, okay? And by the way, you sometimes have a halo around companies. Google, right? They miss the social media. I'm recorded. They miss so many things. So many big companies have missed so many things. I feel pretty good with Intel. I mean, we've done some stupid stuff, okay? We came with Open3, MP3 player before iPad. We came with cloud computing way before Amazon, thought about that. It was burned in a fire, and we just thought, okay, we don't reconstruct it. Okay, so you know the story, okay? So yeah, we've done lots of stuff, okay? The core business of Intel is CPU, okay? Which brings me to the next question, right? Inference, right? Inference is like a huge hype today. Where most of the inference in the world happens, do you know? Not on NVIDIA GPU, okay? 80% of the world inference, okay, AI inference, happens on CPU. Okay, that's a fact, okay? Just to let you know. So there's a huge hype, okay? And sometimes
of the workload, not the amount of computation. I need to be specific about it. The workload itself.
You're talking about the cycle.
Exactly.
So you might say that 90% of the world code is written in Python, but 90% of the world code,
exactly,
the cycles that are running on a machine is actually C++. Okay, so it's different. But we do see new usages. Look, the laptop has definitely gone into some incline, okay, due to multiple reasons, okay? First of all, okay, it's a marketing question. I don't care about that. But for example, the next generation of our CPUs will have a VPU, which it has a neural network accelerator inside, okay? And people are learning what to do with it, okay? So the whole face recognition or stuff that you do want to do with your, and today, everything's neural networks, right? And Google are doing 90% of what they're doing with neural networks. So yeah, we get it, such accelerators into the CPU. Okay, so it was a very long answer. I don't know if I.
Okay. It seemed to me that the oneAPI project seemed to tell new startup, hey, use this oneAPI, use SYCL. Okay, you can run on NVIDIA, you can run on everything, but your point is that in the near future, I don't know when, we will have a GPU that will compute in NVIDIA, and then the startup, when they want to go to production, will say, hey, I have option. I have Intel, I have and I have NVIDIA, instead of from the beginning integrating using CUDA, and then you can go on. This is the point of the oneAPI, right?
It's one of the points.
open standard, right?
It's one of the points. Look, it's open standards. By the way, you can influence the standards. You can go to GitHub and go to the meetings and see where the next meeting is, actually zoom in and affect the standard. Okay, and we're working with people from all around. Well, I mean, if you look at the oneAPI tab, okay, technical advisory board, you'll see here there are people from Amazon, from Microsoft, from Google, from all around. Okay, and we're talking to lots of our competitors as well to make this happen. I feel like this is a great initiative, green initiative, right? If you want, for the benefit of everyone. Yeah, it started with, like you said, the ability to port code from everyone to everyone, or from NVIDIA to Intel, and yeah, NVIDIA are doing great things. I like what they're doing in many aspects.
But they are proprietary.
They are proprietary. They and they don't want to break it. And by the way, Apple are doing the same. There's a huge advantage where you can design the whole thing from the ground up. You have the software, the firmware, everything. It gives you a huge flexibility, right, to create your own features and everything. And this is what Apple is doing. It's working great for them. Okay.
So in this regard, we have like we gotta answer here to two questions. At the beginning, someone asked about the performance, and now we've been asked about the open standard. And I think that anyone that is in the oneAPI initiative, and I will include OpenMP in this, would say there is a trade-off between those two. Meaning that when you get, come again?
Robustness versus
of course. And when you got your hardware with your compiler and your language and your directives and things like that, obviously you control the entire ecosystem on one hand. But on the other hand, as you said, the word today is open to competition all the time. And you get different hardware, different software from different vendors. And the oneAPI initiative in this regard is standard based. And that's the reason why we actually even talk about it in academia. Because I think I wouldn't teach you about CUDA because that's a proprietary thing. But when we talk about SYCL and OpenMP, as Guy said, there is an advisory board of all the companies around that, because this is not, SYCL is not of Intel.
No, it's a Kronos.
OpenMP is not Intel. It's of all of the vendors. And you can influence, and it's open source, and in that regard, it's like talking about C++. So obviously it comes with degradation in performance. And I can tell you that over the last 5-6 years, we saw that this gap is almost been bridged in SYCL and in OpenMP. I think that I showed you in OpenMP something about that. And in SYCL, it's almost there. It's almost there.
So yeah, and I said that one thing you have to remember when you're dealing with highly parallel, highly heterogeneous stuff, okay, and you want to get the last picosecond of performance, you have to know more about your hardware. It's not like you can just lift the software and throw it anywhere. It will work, but again, it depends on the exact kernel. It can run poorly. Sometimes you need that. Now you don't want to need that because you don't want to deal with the gory little architectural differences and stuff. but sometimes I still don't see any way. Now AI will get into that, and I'm sure we're at any level we're trying to use AI. I mean, and you can see that right now in the cloud, how we, companies like Granulate, I don't know if you heard about them, they know how to, they listen to your workloads, and they know how to better manage the resources, and it's going to happen in all levels, okay? And we got it in hardware today in CPU, right? How many threads is better for you? And you talked about that, right? So yeah, performance portability, and I mentioned it, is sometimes a different story, but it really, really depends on what you need.
So C++ 17 execution class as part of the standard library. So I don't know, but I think many companies will only allow their developers to use very trustworthy libraries, and sometimes only the standard library in the big legacy code. So how can developers trust the SYCL libraries and not use the simple execution policy?
First, like God said, the SYCL is a standard driven by Kronos Group. So it's a big group, that drove OpenCL and SPIR-V and many other standards. Okay, so it has a father. It's not an orphan. There's going to be some compliance. You can know that it's working, and I don't know. There's lots of compilers in the market, like I showed. Some comes from the academia, some are commercial.
Is there a cooperation between the language people, like the standard PDB, and oneAPI?
Yeah, so we're talking to the C++ committee, and I
Can you cooperate to add that SYCL is here over the last 10 years? It's just been a part of Intel because it's been already established over the last 10 years.
right, but it takes
It's like
time. It
huge
always
idea.
takes time to establish. For me, like you said, I totally agree. I wish C++, ISO would include all of these, and yeah, there are talks about that. There's a suggestion by NVIDIA to C++ 23 to add all kind of heterogeneous stuff. So there's lots of things going on. By the way, there's a huge community in Israel of C++ developers. Okay, when you have time for that, people who really into the thing. There are conferences around it here. But yeah, I totally agree. Now, when you take pandas code or whatever Python library, do you know who generated it? You just trust them, right? I mean,
Yeah, I mean, not me personally. I mean, like,
I got you.
the company.
I totally understand. So, like I said, compliance, adoption, and eventually results. This is what makes people confident and adopt stuff.
So in software updates, I saw there more than ever like ASICs on the die that do very, very specific things. Like you would never think of putting that on a die a few years ago.
Absolutely.
And I'm wondering if there's like cooperation or plans to integrate like these new ASICs into the software stack to be supported by oneAPI. Is this like a part of the plan, or is it just a?
It's not part of the plan. It's already implemented. Okay, so today you purchase the software app and you run PyTorch. Okay, we're already, and I did that. Or TensorFlow. We're already using AMX. Okay, you don't have to care about it. That's what's nice about it, right? We're upstreaming, okay, to PyTorch and to TensorFlow, right? For me, the best case scenario is that you don't even know that Intel has 20,000 engineers, okay? Just git, pip install PyTorch, run PyTorch. It works on NVIDIA, it works on Intel, including all the latest and greatest, acceleration, like AMX, for example. And it's working, by the way. It's working.
I would like to jump in because this is a very recent paper that's been published in Los Alamos. Specifically, it's not been shared. Sorry, I think that would be a tremendous reference. Here we go. So that's on my part. So oneAPI actually been designed specifically, as Guy said, to this purpose. And what you see here is the first ever reported results from academia. In this case, it's the new supercomputer that's been built as a subsystem in Los Alamos, entirely software rockets. And they have done, and with no change to code, they took 2 legacy codes, very well structured, and a real production code. In those cases, one is multi-physics, multi-material, and the other one, I think it's a flow thing. And without any kind of change to the code, any kind of change, no SYCL, no OpenMP, no nothing, just compiled it with oneAPI to these software rockets with and without high bandwidth memory, and compare those to Haswell, right? It was Haswell. And what you see here is the percentage of improvement that they got by instruction. But you can see here right over here, right here, you can see the improvement that they got to the benchmarks, the real benchmarks, with HBM software rocket. That's the improvement in regard to this, and that's without the high bandwidth memory. And what you see is about almost an entire order of magnitude improvement because of those parts to numerical calculation. This is physics, numerical calculation basis mostly, and that's kind of improvement. It's like it used to be like 20 years ago, and now that's the first time that we see that again because of that change.
So this is actually a great question. Okay. AMX, okay, is a 2-dimensional register, right? And it's not easy to use, right? If you actually want to code for AMX, you know, it's a different way to program, and I don't care about that. To be honest, I don't care. I'm running PyTorch, I'm running TensorFlow, just run it faster using this acceleration. And this is a great example. I don't want to do that. I'm an AI researcher. Okay, and this is great because we're working on that like 2-3 years now to enable it. And once the hardware is out, the software is supporting it seamlessly. You don't even have to know. And you just see and you know it can be 4x faster if you use AMX on this specific workload.
You mentioned that Intel CPU in the future will have dual network accelerators. So from personal experience, when you offload a job to a GPU that's connected via PCI Express, the overhead that offloading the job GPU is very large, and most often than not makes it run slowly. So will offloading jobs to accelerators that are on die or on package be significantly faster? And if so, will it make it so most cycles spent inferencing will be spent on VPUs instead of on CPUs? And how does AMX time?
So first, you're totally right. There's always an overhead, right? So building a heterogeneous software, you have to make sure that the overhead of taking the data back and forth worth it, okay? And I try to show it to you with little examples of, the buffers where it's all hidden from you, and the runtime knows when, but it doesn't always worth it, right? If you're doing only one iteration, it doesn't make sense to copy the data back and forth. Okay, and I showed you that Intel Advisor can actually take this into account, take the overhead into account. Now, if you're on die, okay, it all happens faster, okay, because the communication, they're using the same, they're sharing the cache, okay, so it's faster. The branching could happen earlier, right? I just showed you the whole pipeline, right, where you get eventually to the header to do 1 + 1, whereas if you're using a VPU for face detection or something for secure login, you don't even have to go like that. You can go directly from the camera, right, through a dedicated pipeline to this accelerator, okay, even if it's on die, okay? So first of all, there are multiple paths to access. Second, it looks different, it's faster, it shares the cache, okay? And like I said, if you have the right usage, we'll integrate it in. For Intel, to take a piece of silicon that is worth millions, if not billions of dollars, to every, I don't want to say millimeter, because every micron costs a lot, okay? And now you tell me, okay, get in AMX, okay? It's a huge piece of silicon, right? And then comes a marketing guy and say, yeah, it's going to be great because this guy enjoy it, but only 5% of the world is using it. And I'm selling this to everyone, right? Think about that, okay? So these are the kind of questions we're constantly asking ourselves, okay? A very interesting thing that happened today is the whole chiplet thing that we can just glue together chips, okay? And then it will allow us to, give you more flexibility in the hardware, okay? And we talked about Google. Google tried to come up with open hardware, like design your own phone, something like that. It never works. But in the near future, you're going to see all kind of flavors because we'll have this flexibility to add more AMX. Give me more AMX because I'm doing this workload. Give me more, GPU. Give me more VPU, stuff like that. So the hardware will be a little bit more flexible as well. I hope I got to your question because it took me
I will
all kind of places.
I will add something that someone asked from Zoom, and I think it's connected. What about the shared memory between CPUs and GPUs? How that changes in regard to this question?
So today in our CPUs, they're sharing the level 3 cache. I think it's a level 3 cache. And you've seen our SYCL, the SYCL implementation allows you to see one unified shared memory space, okay?
But none of us actually saw Ponte Vecchio, for example, in actual work with shared memory. That still
we haven't. No,
we haven't.
Either
an expectation,
the dates. We will see.
The date.
Look, we after this course, they all understand that memory is sometimes in such workload is more important. Okay, look,
and compute.
GPT-3, okay, for example, I think only the Onyx model is 10 gig. Okay, now there's no way you can have 10 gig on die, right? So you have to thrash it back and forth. So yeah, this is one of the main problems today. And like I said, we're putting together on die CPU and GPU, and going to see more flavors. At the Sapphire Rapids space, what we call Falcon Shores, you're going to have multiple such huge dies, okay, and everything on die, right? With communication overhead reduced significantly, but by the problem is by that time you're going to have GPT-10 or something, right? And you're going to need more. But that's good. We all have work for that future.
Any further questions? Thank you very much.